Hello students, thank you for watching and welcome to the lecture video for the course Statistics for Management 2. This lecture video is prepared by Instructor Grima, the Department of Business Management in Pharma College. Before we get forward to the description of this course and the first chapter of this course, let us recall the definition of statistics and managerial functions. In Statistics for Management 1, you remember that statistics is a science or a process of collecting, organizing, presenting, analyzing, and interpreting data to assist decision making. On the other hand, managers are professionals who are responsible to perform managerial functions. The 5 vital managerial functions are planning, organizing, staffing, leading or directing, and controlling. Even if decision-making is not stated as one vital managerial function, but decision-making is a common core managerial function, i.e., there is decision-making in planning process as well. There is decision-making in organizing process. The same is true for staffing, leading, and controlling. Since managers either at top level or middle level or low level, managements are responsible for decision making. They are expected to have reliable information which enables them to identify the best alternative, the best solution, the best strategy, the best policies, and extra. Therefore, the science of statistics is very important for managerial functions because in statistics we find 5 major statistical investigations that help us decision-making process. These 5 statistical investigation stages are organizing of, collecting of the data, then organizing them in terms of tables, graphs, and statistical charts, as well analyzing them, interpreting them, and finally providing a useful statistical information for managers and other interested parties. Therefore, in the meantime, we need to acknowledge that statistics is a very important science or discipline for managerial functions. Students of business management are expected to be managers of different companies. As well, they are expected to be business researchers in different companies or organizations, including government entities. Therefore, statistics for management is important course for business management students, and this Statistics for Management 2 introduces sampling and sampling distribution of mean and proportion and their application in business. The course will also introduce hypothesis testing of population mean, hypothesis testing of population proportion. As well, this course introduces to the students about the concepts of statistical estimation of population mean, statistical estimation of proportion. The course also introduces to the students about the concept of variance of analysis, which is known as ANOVA. And finally, the course introduces to the students about simple regression analysis and the correlation. Therefore, the objective of Statistics for Management 2 is to enable students to have a knowledge about the application of statistical tools in the managerial decision-making process. To this end, we are going to deal with 5 chapters. Let us start with the first chapter. Chapter 1 is about sampling and sampling distribution. In this chapter, we are going to introduce sampling theory and the concepts, and then we are going to deal with sampling distribution of mean and the population proportion. Let us start with the first lesson of the chapter, i.e. sampling theory. The first concept that we need to know regarding sampling is the definition of sampling. Sampling is a process of selecting sample from a population, which means a process of selecting some members of a population, some individuals, some companies, some entities from the overall population is considered to be sampling. And the sampling is widely used in business as a means of gathering information about the population. In order to have information about a population, in order to organize, present, analyze, and interpret a data about a population, a researcher or a statistician is required to select some individuals, some entities from the population for collecting data, so that a means of gathering useful information about the population is considered to be sampling. In statistical investigation, the data that we are going to collect, that we are going to organize, that we are going to present in terms of statistical charts and graphs, and that we are going to analyze, and finally, that we are going to interpret, is collected in terms of 2 ways. And the process of gathering data from a target population is considered to be survey. Survey can be classified into 2 major classes. The first type of survey is known as census survey. In census survey, the statistical investigator or the business researcher will cover all population, so that every element of a population will participate in the data provision process. The second type of survey is considered to be sampling survey. Sampling survey is a kind of survey that covers a part of a population, so that in sampling survey, first we try to select a sample from a population, then we start to collect or gather data from a sample, so that there are two mechanisms by which data can be collected for a statistical investigation, and those are census survey and the sampling survey. When we compare sampling with census, we find sampling as a preferable or a better type of survey. This is because of the following reasons. The first reason why sampling is preferable is because of in sampling we can save money. When we are collecting data from only some portion of a population, the cost that we incur in this process can be minimized. At the same time, we can also save a time. Within a short period of time, we can be able to gather data from a sample as compared to population. And for a given resources, the sample can also broaden the scope of the study, and a more detailed information can be collected using a sample. Sometimes, the research process or statistical investigations may be destructive. And in this process, sample can save a product that we are going to investigate, that we are going to test. If accessing the population is impossible or it is difficult, our only option is trying to take a sample and trying to collect the data. Finally, in sampling survey, we can interview many individuals who are a part of our sample as best as possible. We can also supervise our process of data collection because of we are asking or we are collecting data from some portion of a population. These are the advantages of using sampling as compared with census. Let's get forward to the reasons for why business researchers take a census. Under two circumstances, business researchers conduct a census survey rather than a sampling survey. This condition is when they have adequate time, as well as when they have adequate money or finance. Business researchers can conduct a census. The first reason why census survey is better than sampling survey is, number one, it enables business researchers to eliminate the possibility that by chance a randomly selected sample may not be representative of the population. At the same time, for the safety of the consumer, business researchers or statistical investigators conduct a census survey. Those are reasons why business researchers look for a census survey. Let us deal with the definition of population and a sample. In a statistical investigation, data is collected either from a population or from a sample, so that we need to know the definition of population and the sample. Let's begin with population. Population is a group of people, items, units, individuals, or entities under statistical investigation. On the other hand, sample is a portion of a population, a portion of, items or units under investigation, so that we can obtain a sample when we are collecting data only about some members of a population. In statistical investigation, we also need to know sampling frame. Sampling frame is the list of individuals, institutions, companies, or entities from which the sample is taken. For example, electoral register, postcode address file, telephone book are considered to be a sampling frame because of they present the list of individuals, companies, entities from which a sample is going to be taken. The other concepts in statistical investigation are parameter and statistic. Let us deal with parameter. Parameter is a statistical result computed to describe the population. Therefore, when we are calculating descriptive statistics like mean, median, mode, at the same time when we are computing the measures of variation like by using range, variance, standard deviation, and if the data we have used to compute those statistical results were obtained from the population, these results are considered to be a parameter. So that parameter is simply statistical results that describe the population. Sometimes it is difficult or it is impossible to collect the data from all members of a population, so that we try to select some portion of a population as a sample, and we use sample data and we start to calculate some statistical results, so that statistical results calculated by using a sample data are considered to be statistics. So that statistics is a statistical result that describes a sample. Let's get forward to sampling methods or sampling techniques. Sampling is a process of selecting a sample from a population. To do this activity, we have two mechanisms, so that there are two main types of sampling. These are random or probability sampling and non-random or non-probability sampling. In random or probability sampling, a few units of a population have the same probability of being selected into the sample. However, in random or non-probability sampling, every unit of a population do not have the same probability or chance of being selected into the sample. Let's deal with the types of random sampling techniques and non-random sampling techniques. Let's begin by the techniques considered to be non-random sampling or probability sampling. The first type of random sampling technique is simple random sampling. In this technique, each unit of the frame is numbered from 1 to capital N, where capital N is the size of the population. Then a table of random numbers or a random number generator software or program is used to select n items into the sample, where small letter n is sample size. This technique is easier to perform on small population than on larger population because of we need to number every element of a population. At the same time, we need to construct a table of random numbers, or we need to even use random number generator, so that it's difficult to apply this technique when population is large. The second type of random sampling is known as stratified random sampling. With this method, the population is divided into an overlapping subpopulation called strata. Then the researcher extracts a random sample from each of the subpopulations. Internally, strata should be relatively homogeneous. However, externally, strata should be heterogeneous, which means every member of a strata is or are homogeneous. However, when we compare the subpopulations called strata or stratum with each other, we find a difference among themselves, so that strata should contrast with each other. The process of creating or dividing a population into strata is considered to be a stratification. This stratification is usually done on the basis of geographical variables. For example, a researcher may use a sex as a criteria to stratify a population into strata, or he or she may use socioeconomic class, or geographical region or location, religion, or ethnicity for constructing strata, or for dividing population into subpopulations, or the so-called strata. The main reason for why business researchers use this kind of sampling technique is that it enables them to reduce the sampling error. The third type of probability sampling is known as systematic sampling. In systematic sampling technique, every case item is selected to produce a sample size of n from a population size of capital N. In order to obtain the value of k, which is sometimes known as sampling cycle, we apply this formula, i.e. k is equals to capital N divided by small letter n, where k is the size of interval for selection, small letter n is sample size, and the capital letter N is population size. This sampling technique is used because of its convenience and because of it is relatively easy to administrate the sampling process. The final human type of probability sampling is cluster or area sampling. Cluster or area sampling involves classifying the population into non-overlapping areas or clusters. This also identifies clusters that tend to be internally heterogeneous, so that clusters are subpopulations that involves items or individuals or entities that are internally heterogeneous. On the other hand, when we compare clusters with each other, they are homogeneous, so that clusters are externally homogeneous, similar to each other. On the other hand, clusters are internally heterogeneous, which means they involve items that are different from each other. As an example of clusters, We can take town, can take company, or homes, college, universities, areas of a city, or geographical regions are considered to be typical examples of clusters. After randomly selecting clusters from the population, the investigator either selects all elements of the chosen clusters, or he or she may randomly select individual items into the sample from the clusters. Clusters are convenient to obtain, and the cost of sampling from the entire population is reduced because of the scope of the study is reduced to the clusters. The second class of sampling techniques is known as nonrandom sampling. In nonrandom sampling, we find 4 types of techniques or methods. These are: number 1, convenience sampling; number 2, judgmental sampling; number 3, quota sampling; number 4, snowball sampling. Let's begin by convenience sampling. Convenience sampling is a sampling technique whereby elements for the sample are selected for the convenience of the researcher. The researcher typically selects elements that are convenient for himself or for herself. This means he or she chooses elements that are simply available, nearby, or willing to participate in the data providing process. The second type of nonrandom sampling is known as judgmental sampling. Judgmental sampling is an improbable sampling technique which occurs when elements selected for the sample are chosen by the judgment of the researcher, so that a researcher will first judge about items or individuals or entities or companies who are going to be elements of a sample, so that a basic determinants of sample in the meantime is the judgments or the professional judgment of a researcher or investigator. Usually, professional researchers believe that they can obtain a representative sample and they can reduce its sampling error by using or taking sound judgments, which will also result in saving time and money. Let's get forward to the third type of nonrandom sampling, which is quota sampling. In this sampling technique, certain population subclasses such as age, gender, or geographical region are used as a strata. The researcher uses a nonrandom sampling method to gather data from one strata until the desired quota of a sample is filled. Quotas are usually filled by using available, recent, or applicable elements. Quota sampling can be useful if there is no sampling frame for the population, so that in quota sampling, the researcher will first determine whether there is sampling frame or not for the population, and if he determines that there is no sampling frame, there is no list of elements or items of the population, he or she is going to apply quota sampling. Try to determine a quota, then he tries to select items until this quota is filled. The final type of non-probable sampling is known as snowball sampling. In this sampling technique, survey subjects are selected On the basis of referral from other survey respondents, the researcher first identifies a person who fulfills the profile or requirements of subjects under investigation. Then he or she asks this person for the names and the location of others who would also fit the profile of subjects wanted for the study. Through these referrals, survey subjects can be identified as cheap as possible, as efficient as possible, which is useful when survey subjects are difficult to locate. These are the four main types of probability sampling and non-probability sampling techniques. Let's deal with the other concepts of sampling, which are sampling error and non-sampling error. When we collect data from a sample, we commit two types of errors. The first type of error is known as sampling error. This error is committed by researchers when the sample is not representative of the population. On the other hand, non-sampling errors are committed by investigators or by researchers because of different reasons that are not related to sampling errors. Those non-sampling errors are like errors of missing data, recording errors, errors of input processing, when a researcher feeds the collected data into the computer, error of analysis, error of unclear definitions, or when a business researchers prepared and distributed a defective questionnaire, he or she will commit errors, and error of poorly conceived concepts are also considered to be non-sampling errors. Generally, when sampling error happens because of the sample is not representative of the population, but other errors or mistakes that are not related to sampling errors are considered to be non-sampling errors. The second lesson in chapter 1 is sampling distribution. Let us start with sampling distribution of mean or X bar. The sample mean is one of the common statistics used in the inferential process. We do have a central limit theorem which states if samples of size n are drawn randomly from a population that has a mean of mu and a standard deviation of sigma, the sample means or X bar are approximately normally distributed for sufficiently large sample sizes, which is n is greater than or equal to 30. Regardless of the shape of the distribution, if the population is normally distributed, the sample means are normally distributed for any sample size. In mathematical formula, we can show the mean of the sample mean as the population mean, so that the mean of sample mean, mu of X bar, is equal to population mean. And the standard deviation of the sample means, which is usually known as the standard error of the mean, is the standard deviation of the population divided by the square root of the sample size. In mathematical formula, sigma of X bar is equal to sigma divided by square root of n. This is the concept of central limit theorem that we will apply in sampling distribution of sample mean. In sampling distribution of sample mean, we use that formula to compute statistical results from a given data. And the Z formula is Z is equals to X bar or sample mean minus population mean or mu all over sigma divided by square root of n. Let us deal with one example in order to be familiar with the application of this Z formula and the sampling distribution of mean. Suppose that the mean expenditure per customer at a tire store is $85 with a standard deviation of $9. If a sample of 40 customers is taken, the probability that the sample average expenditure per customer for this sample will be $7 or more is computed as follows. In this scenario or example, the sample size, which is 40, is greater than 30, so that we can apply the central limit theorem. Because of the central limit theorem, the status sample mean are approximately normal distribution if a sample size is equal with or greater than 30. Therefore, the sample means are normally distributed, and in this scenario, population mean or mu is $85. When we get back to the given data, here we find the population mean of $85. Population standard deviation is $9. When we apply the Z formula for this sample mean, that is equals to sample mean or X bar minus population mean or mu all over sigma divided by square root of n. When we insert the given data instead of variables in this formula, it's $7, which is sample mean, minus $85, which is population mean, divided by $9, which is population standard deviation or sigma, over square root of 40, which is sample size. Then 2 divided by 1.42, and finally the result of this formula is 1.41. Therefore, that value is 1.41. From the normal distribution, or from the so-called from the Z distribution, which is stated as table A5, Z is equals to 1.41 results a probability of 0.4207. Let us look at this table A5, a normal Z distribution. We need to remember Z score is 1.41, so that we try to find the probability at this value. This is Z distribution, and we try to take 1.4 row here. Since the Z score is 1.42, we try to select, Since Z score is 1.41, we select 0.01 element, this element, and 1.4 row. This intersection point of this row and this column yields 0.4207, so that the probability at Z score of 1.41 is 0.4207. This number is the probability of getting a sample mean between $87 and $85, the population mean. When we solve for the tail of the distribution, we finally obtain 0.0793, which is the probability of sample mean, or X bar, is greater than or equal to $87. That is 7.93% of the time, a random sample of 40 customers from this population will yield a sample mean expenditure of $7 or more. Or we can show this problem and the solution in terms of graph or diagram as follows. This is the normal distribution, and then the middle of this distribution, that score is 0, but at the sample mean of $87 Z square that we have calculated previously is 1.41, we state here, and the probability of each tail is 0. Each tail is 0.5, and here 0.5, so that we are calculating the probability that X bar or mean is equal with 87 or greater than $87, so that $87 is around this, so that our region here is this part, X bar is equal with 87 and greater than 87. Since the probability of this tail is 0.05, therefore the probability of X bar is $87 or greater than $87 is calculated by subtracting the probability of this region from 0.05, so that the probability of X bar will be between 85 and $87 is 0.4207, and the probability of this right tail is 0.05, so that the probability of X bar is equal with 87 or greater than $87 is determined by subtracting 0.4207, the probability of this region, from 0.05, and finally we obtain 0.0793, so that we can show in terms of diagram in this manner. Sometimes a researcher may have a finite population, or the number of population may be limited or it may be known, so that in this case a statistical adjustment is need to be made to the Z formula for the sample mean. This adjustment is known as finite correction factor, which is square root of capital N minus small letter n divided by capital N minus 1, where capital N is population size, small letter n is sample size. It also operates on the standard deviation of sample. This the formula for sample mean of a finite population is finally used to calculate Z value, or calculated Z value. Z is equals to sample mean or x bar minus mu or population mean divided by sigma over square root of n times square root of capital N minus n over capital N minus 1, so that when our population is finite, when we know the number of population, we apply this adjustment, and finally we apply this adjusted Z formula for our sample mean. Let us deal with this sampling from a finite population with one example. Suppose that a production company's 350 household employees average 37.6 years of age, with a standard deviation of 8.3 years. If a random sample of 45 hourly employees is taken, the probability that the sample will have an average age of less than 40 years will be calculated as follows. In this case, the population mean is 37.6. The population standard deviation is 8.3. That is, mu is 37.6, sigma is 8.3. The sample size is 45, but it is being drawn from a finite population of 350. That is, sample size or n is 45, population or capital N is 350. The sample mean under consideration is 40, or x bar is 40, so that we can show this problem on a normal curve as follows. This is normal curve or normal distribution, and the population mean or mu is 37.6 here. We state the center of this normal curve. X bar or sample size, x bar or sample mean is 40. Then we get forward to Z value or Z calculated value. Our formula is Z is equals to x bar minus mu all over sigma divided by square root of n times the square root of capital N minus n over capital N minus 1. When we insert the given data in this formula, Z is equals to 40 minus 37.6 divided by 8.3 over square root of 45 times square root of 350 minus 45 over 350 minus 1. This yields 2.4 divided by 1 minus 157. Finally, the value or the calculated result is 2.07. We try to locate the probability at this that value or at 2.07 from statistical table. Let us deal with the table. Our value is 2.0. The value is here, 2.07. So that we look at this table. These tables we look at, 2.0 row, 2.0 row, and we look at 0.07 this column, this column. We find this the probability in this column. Therefore, the intersection point of 2.0 row and the 0.07 column is 0.4808, so that this is the probability at Z value of 2.07. Therefore, the probability of getting a sample average age of less than 40 years is the sum of 0.4808 and 0.5, which is 0.9808. Let us proceed to sampling distribution of proportion or p-naught. Sometimes, in analyzing a sample, a researcher will choose to use a sampling proportion which is denoted by p-naught, whereas the mean is calculated by averaging a set of values. The sample proportion or p-naught is computed by dividing the frequency with which a given characteristic occurs in a sample by the number of items in the sample. Can state in terms of formula, sample proportion or p-naught is equal to x divided by small letter n. This formula, p-naught represents sample proportion, x represents number of items in a sample that have certain characteristics. Small letter n is number of items in the sample or sample size. A researcher uses this sample proportion in the statistical investigation by applying a central limit theorem to this sample proportion, in that the sample normal distribution approximates the shape of the distribution of this proportion. If n times p is greater than 5 and n times q is greater than 5, which means p is the proportion of a population and q is calculated by deducting p from 1, so that the sum of p and q is equal to 1 or 100%. The mean of sample proportions for all samples of size n randomly drawn from a population p, or the population proportion, and the standard deviation of sample proportion is square root of p times q over n. This is sometimes known as the standard error of the population or the standard error of the proportion. Sample proportions have a Z formula, so that whenever the result of n times p is greater than 5 and n times q is also greater than 5, we can apply a central limit theorem and we can compute z value by using this formula. Z is equals to sample proportion or p-naught minus population proportion or p all over square root of p times q over n, where p-naught is sample proportion, n is sample size, p is population proportion, and where q is calculated by deducting p from 1. Let us deal with one example to be familiar with sample proportion. For example, if we assume 10% of a population of parts or products is defective, the probability of randomly selecting 80 parts or products and finding that 12 or more parts are defective can be calculated as follows. In this scenario, population proportion is 0.10 or 10%. Sample proportion is calculated by dividing 12 by 80, which is 0.15. And in this case, sample size or n is 80. When we enter these values in the Z formula for sample proportion, it will be Z is equals to 0.15, which is a sample proportion, minus 0.10, which is population proportion divided by square root of P times Q, or 0.10 times 0.90. Here, Q is 0.90. To obtain this result, we use the formula of Q is equals to 1 minus P. So that Q is equals to 1 minus 0.1, which yields 0.9. Then we divide the result by 80, so that this yields 0.05 divided by 0.0335, so that the final result of Z value is 1.49. By the same fashion, we search the probability at Z value of 1.49 from the normal distribution table, and let us look at the probability at Z value of 1.49. This is the distribution, and we first determine the row. Since the Z value is 1.42, 1.54 is the row that we need to look at, and the 0.09 is the column that we need to look at. The distanciation point of this column, or 0.09, and this row 1.4 yields 0.4319, so that the probability at the value of 1.49 is 0.4319. And this table gives a probability of 0.4319 for a Z value of 1.49, which is the area between the sample proportion 0.15 and the population proportion 0.10. Therefore, the probability that the sample proportion, or P naught, is equal to or greater than 0.15 is determined by subtracting the probability at the value of 1.49 from the probability of one tail, which is 0.5, so that we obtain 0.0681, which can be interpreted as about 6.81% of the time 12 or more defective parts would be in a random sample of 80 parts of products when the population proportion is 0.1 or 10%. If this result is actually occurred, 10% proportion for population defects would be open to the question. We can show this problem and the solution graphically as follows. Here, this is normal distribution. At the center of this distribution, population proportion of P is 0.1, and Z value at population proportion is here 0. Sample proportion is 0.15. That value at sample proportion, is about 1.49. The probability of this right tail is 0.5, and the probability of sample proportion between 0.1 and 0.15 here from this up to this is determined to be 0.4319 from the table. Therefore, the probability that sample proportion, or P naught, is greater than or equal to 0.15 is determined by deducting 0.4319 from 0.05 from 0.5, which is 0.0681, so that we can show diagrammatically this problem, including the solution by this normal distribution in these ways. This is all about the first chapter, so that in this chapter we have looked at sampling distribution as well as sampling theory. I hope we have obtained the knowledge about sampling theories and sampling distribution of, population mean and proportion. I hope all the best for your study time, and I hope we will meet with other video in chapter 2, which is about statistical estimation. Thank you very much for your attention, and try to study as well and try to solve exercises that are presented in the first chapter of this course. Thank you very much.